Nowadays, when we think of the origins of the calculus, two names inevitably spring to mind. Newton in England. Their achievements were only made possible because of numerous predecessors dotted around Europe. They, in turn, reflected a rediscovery and extension of problems studied by the Greeks. We also think of the calculus as being concerned with the mathematical description and analysis of change, and so it is. In a sense, it grew out of problems of motion, problems like the orbit of a planet and the path of a projectile. But it's also about simpler static problems, about finding areas under curves and their volumes when rotated, about tangents to curves and lengths of arcs, about their centers of gravity. These 5 problems, raised by the astronomer Johann Kepler, exercised mathematicians throughout the 17th century and form the mathematical basis of the early history of the calculus. The earliest rigorous determinations of such areas and volumes are Greek. The area for a circle was argued, if not actually discovered, by using the method of exhaustion. That method involves comparing the area with better and better fitting inscribed polygons. Subsequently, the formulae for the surface areas and volumes of spheres and cylinders were discovered by Archimedes. The method Archimedes used to discover these results was different. He regarded areas as made up of lines and volumes as made up of slices. This method, and others like it, were independently rediscovered at the start of the 17th century and came to be called the method of indivisibles. The account of the subsequent developments leading up to the work of Newton and Leibniz is provided by Professor Boyer of Brooklyn College, New York.
Ideas often are like hardy spores that reappear every now and then without any apparent reason. And this concept of the indivisible, which Archimedes had used, was such an idea. We did not have the work of Archimedes involving this, and yet the same concept reappeared in the 14th century in the work of Arame when he was plotting the latitude of forms, that is, of variable quantities. It reappeared also in southern Italy, especially in the work of Galileo. Galileo had been studying the path of a projectile, and he had shown that a projectile, if you disregard air resistance, will travel in a parabolic path. And hence he was interested in the area of a parabolic segment and used various infinitesimal methods to find areas of the parabola and other curves. He had intended to write a little work on what he called infinity and the infinitesimal, but he never got around to it, and it remained for one of his students, Bonaventura Cavalieri in particular, to write a famous work which was published in 1635 and called Geometry through Indivisibles. He also had another student, a young scientist by the name of Evangelista Torricelli, whom you probably recall for the invention of the barometer. But Torricelli also was an excellent mathematician, and he was interested in studying curves by the method of indivisibles, and in particular studying a new curve that Galileo had noticed. Galileo was fascinated by the curve which you will obtain by taking a spot on a circle and then let the circle roll along a straight line, watching the spot as it traces out a curve. This was the curve known as the cycloid, which possibly the Greeks had known, but we have no clear evidence that they had noticed this curve, which of course will have infinitely many arches if you will allow it to continue. Galileo hoped to find the area under one arch of this curve, but was unable to do so directly. He therefore used an indirect method. He sketched one arch of the cycloid, cut it out of a uniform material, and weighed this pattern against the weight of a unit area of this material, and said he thought the area under this curve was just about 3 times the area of the circle that had generated the curve. He also suggested that this was a beautiful curve architecturally, and suggested that it be used in the construction of bridges.
The Ponte di Mezzo in Pisa was indeed constructed with cycloidal arches by Galileo's pupils after his death in 1642, and it still survives. His attempts at measuring the area under the cycloid curve, however, were soon to be superseded by the work of several other European mathematicians who followed him.
There were no daily newspapers or scientific journals to carry the message of what Galileo and Torricelli were doing, but fortunately there was a Mennonite friar by the name of Mersenne in France who served as the universal correspondent of scientists in Europe, and he told the French mathematicians what the Italian mathematicians were doing. In particular, he told Roberval, a French mathematician, of the work on the cycloid, and Roberval became fascinated in this problem. Roberval wrote a treatise which was published only after his death, because he held a university position which required him to compete for the continuation of his position with other mathematicians, and he therefore did not wish to make his methods known. He therefore lost credit, at least in his day, for many of his discoveries, including this discovery on the area of the cycloid.
Roberval's method for the area under the cycloid made use of indivisibles. He began by comparing half the cycloid with half the generating circle. If the circle is thought of as made up of lines, then systematically moving those lines inside the arch produces another curve. This curve Roberval named the companion of the cycloid. If you grant that areas are made up of lines, the area between the companion curve and the cycloid must be the same as the area of the semicircle. Now, to determine the area under the companion curve, we can observe that it is symmetric, and so divides this rectangle into equal areas. The base of the rectangle will be half the circumference of the generating circle, and its height equal to the diameter. So we can now calculate that the area of the rectangle is twice the area of the circle. The area under the companion curve must be equal to that of the circle. So we have the area under the half cycloid as 1½ circles. The cycloid indeed does have an area equal to 3 times the generating circle, as Galileo had guessed, but not proved. This method of considering areas as made up of lines was only one of the methods used at the time. There were others being developed that look far more like our modern approach to integration using strips and rectangles. But for the moment, we turn our attention to the tangent problem.
Torricelli and Roberval found not only the area under a cycloidal arc, but they also found tangents to the cycloid curve. This problem was a very important problem for mathematicians and scientists of the time, and in fact of it, Descartes in his Geometry said the following, and I dare say that this is not only the most useful and most general problem in geometry that I know, but even that I have ever desired to know. The trouble with the method of tangents that Roberval and Torricelli, and also Descartes, who also found the tangent line, was that their method could not be applied to other curves. And it remained for one of their contemporaries, Pierre Fermat, to introduce a method of tangents which is very much like that we use today in the calculus.
We can more or less argue as Fermat did to find a tangent to the parabola y equals x squared. Let's look for the tangent to the curve at the point A, with coordinates a squared, and find its slope. Take a nearby point B on the tangent, whose first coordinate is a plus e. Since the point B on the tangent lies below the point C on the parabola, we know that BD is less than CD, and CD is equal to a plus e all squared. So the slope is greater, but obviously not much greater, than a plus e all squared minus a squared all over e, and that just gives this. Fermat simply dropped the e term. We would nowadays apply a limiting argument, letting B and C approach A as E got smaller and smaller. But however we do it, it's clear that the slope is 2A. In the same way, Fermat was able to look at his so-called higher parabolae and derive the tangents to them as well. He found tangents to y equals x cubed, y equals x to the fourth, and so on. But there was another aspect of his work, the calculation of areas. His results weren't all new, but the method was. Instead of regarding an area as made up of indivisible lines, Fermat considered it as made up approximately of strips. But by arranging for a cunning choice of widths, Fermat was able to convert an area calculation into an arithmetical one, and that made it easy for him. So Fermat had really quite powerful methods for solving area and tangent problems connected with his parabolae, y equals x to the n. He was able to extend these methods to his hyperbolae, where n is negative, and to the mixed curves, where the index is fractional, and these results were new.
Fermat had always hoped to interest his friend Blaise Pascal in his mathematics, and for a while he succeeded. Pascal thought that it was wrong for him to spend his time on mathematics rather than contemplation of the grace of God. But in 1658, Pascal had a toothache. Being unable to sleep, he got up and started to work on a mathematical problem. in this case the problem that everyone else was talking about, the problem of the cycloid, and he found that the toothache disappeared. Feeling that God therefore did not frown upon his pursuit of mathematics, he worked out quite a number of problems connected with the cycloid, the problems that are of importance to mathematicians and scientists, that is, the tangents, the areas, the centers of gravity, and volumes obtained by revolving a segment of the cycloid around some other line. He was so proud of his work that he then challenged other mathematicians to solve the problems that he had solved. And he publicly announced that he would present 2 prizes to the best solutions to the set of problems that he proposed. The publicity was not too good, and so he got only 2 significant replies to the contest. And he made an unfortunate decision. He and Roberval agreed that neither one of the sets of answers was worthy of a prize, inasmuch as one of these sets was sent in by Wallace from England. This redoubled Wallace's dislike of French mathematicians. One mathematician who had thought of sending in a reply but found that the deadline was too close was Christian Huygens, who at the same time was working in Holland on the cycloid from an entirely different point of view, a practical point of view. Galileo had years before noticed, we're told in the cathedral at Pisa, that when the chandelier in the cathedral moved back and forth, that it made no difference whether the chandelier swung in a small arc or in a larger arc, that the period was exactly the same. Now, if you're very sharp with your time concept, you may notice that this is not exactly true. In other words, the simple pendulum is not exactly isochronous, but it's sufficiently close to this so that pendulum clocks are practical. And Huygens then made and sold pendulum clocks. Galileo had had the idea of a pendulum clock, but in his old age he was unable to carry out the project, and he left it for his son, who was unable to get clocks which were satisfactory. So Huygens is regarded as the effective discoverer of the pendulum clock. But Huygens knew that the simple pendulum is not exactly isochronous, and he wished to improve upon his clocks, and mathematically he noticed that whereas this arc in which the pendulum moves is a portion of a circle, that if only he could make it move in an arc which is that of the cycloid, that then it would be truly isochronous, and it would not matter whether you have a large swing or a small swing. But the big problem was to find how to make the pendulum bob move in a cycloidal arc. Huygens discovered a beautiful solution. He discovered that if at the top of the pendulum string you introduce a cycloidal jaw on each side of the string, so that in moving first to the left and then to the right, part of the string will wind up on these cycloidal jaws, then mirabile dictu, this pendulum will actually move in a cycloidal path.
Huygens did indeed build a clock with cycloidal jaws. We have copies of it and of his drawings. But unfortunately the friction of the strings and so on made it no more accurate than other clocks with a simple pendulum. However, he had in the process exposed some interesting mathematics. The curve that you generate by unwrapping a string from round a cycloid is another cycloid of exactly the same size. This construction gives us a relationship between the length of the pendulum and the length of the curve. If the diameter of the generating circle of the cycloid is d, the length of this pendulum, for example, is 2d. So the length of the cycloidal arch is 4d. In other words, Huygens had rectified the curve. But there was, handed down from the Greeks, a dogma in mathematics and philosophy that straight lines and curved lines could not be exactly compared. In fact, even Descartes wrote, "On the other hand, geometry should not include lines that are like strings, in that they are sometimes straight and sometimes curved, since the ratios between straight and curved lines are not known, and I believe cannot be discovered by human minds."
But Descartes presumably made this statement thinking of algebraic curves only, since in his geometry he limited himself to those. But here too, mathematicians found that he was quite wrong. One of Huygens' associates, a young Dutchman by the name of Heinrich van Heuraet, was studying one of the parabolas of Fermat, the so-called semicubical parabolas, and showed very clearly that you can construct with ruler and compasses a straight line segment exactly equal to the length of a segment of this parabola. Interestingly enough, since simultaneous discoveries appear every now and then in the calculus, this same problem was being handled in England, where Sir Christopher Wren, of architectural fame, had discovered also that the cycloid could be rectified. And a young protege of John Wallis had taken the semicubical parabola and had shown that you could rectify a segment of this. The parabola, the semicubical parabola, therefore, often is called the parabola of Neal, because William Neal was this young man who had rectified the curve. This dogma of Descartes that curves could not be rectified was thoroughly demolished by these instances, and it turns out that Fermat published during his lifetime only one part of the calculus. That was the part in which he showed that there are many algebraic curves which can be rectified.
There was one final discovery in this period. Fermat, amongst others, must have noticed an inverse relation between tangents and quadrature. Evidently, the area contained under one parabola is proportional to the slope of the next but one, and vice versa. But Fermat didn't explore this connection in any depth. Perhaps he thought of it as just a coincidence. It was Isaac Barrow, who later gave up a chair in mathematics at Cambridge to become chaplain to King Charles II, who saw otherwise. Barrow's proof, however, retained the old geometrical methods, and not the new analytical ones, robbing it of some of its power. Nonetheless, with Barrow's work, the stage was set for the great consolidation and extension of methods that we call the calculus, and associate with Newton in England and Leibniz on the continent.